Good morning, and this is my first Google Hangouts video for about 10 months, and I'm sure you've all been eagerly awaiting it. What I want to talk about this morning is using AI to play the game of Pong that you've probably seen from many, many years ago that was originally released by Atari. And this is a very familiar example, and I'm not using my own code. I'll say where it all comes from in the notes afterwards. Here we are. So what we've got here, looking at a live demonstration of the game as trained and fully functional, or more or less fully functional. So let's just remind ourselves of what's happening. The original game, as sold by Atari decades ago, was played on a television screen, and each player would have a control which moved a paddle, the left and right hand rectangles, up and down, and the idea is to prevent the ball from going off your side of the screen. And it was very popular. I can remember playing it as long ago as, oh goodness, about 1980, I think. And they sold lots of these. And recently, if you've been following the AI debate, DeepMind trained on these games and managed to become proficient at all of them, not just this one, but Breakout and numerous others. There's a game called Snake, where a snake runs across the screen. You've probably seen them before. Anyway, why is this interesting? Well, at one level, if you're a human being, you look at the screen and you learn how to manipulate your paddle, and that's all the game consists in. You might think that if you wanted to program a computer to play this game, you would need a complicated algorithm that calculated the position of the ball, the little blue square, and the paddle, and moved the paddle accordingly. And the red square here, that's actually what is happening. The red square always manages to hit the ball because it's being told by the computer where the ball is in terms of coordinates on the screen. But the white paddle, which is what you might call our paddle, isn't being given that information. Instead, the white paddle is being controlled entirely from what you might call looking at the screen. The software takes the screen image, feeds it into an artificial intelligence neural network, in this case structured using TensorFlow, and then the paddle is moved in a way that it gradually learns to move in order to hit the ball. And even now, it does occasionally miss. I think it missed then, in which case its score is reduced by 1. But when it hits the ball and prevents it from hitting the side of the window, its score goes up by 1. And you can see that most of the time it manages to hit it. Now, it's very important to appreciate that this is not being done by the machine being told the position of the ball in absolute coordinate terms and therefore calculating where to put its paddle. That's a possible way of solving the challenge, but it's not the way this solves it. And what makes the approach here interesting is that there are two separate parts to this software. One of them is the neural net that actually tells the paddle where to go. And the other one is the design of the game itself. And in theory, you could replace the game design with any game design, feed the same data into the neural net, and learn to play any game. So the implications of this are very important because it suggests that the computer, by reading screen positions, can derive a behavior that solves a real-world problem in real time. And we need to remember that this is just running on a MacBook. Of course, the big machines, the Alpha Zero and the Alpha Go machines, are running on very, very sophisticated, high-powered machines with multiple processors and huge amounts of technological support in order to achieve what they've achieved. But the fact that this can be done on a laptop at all is remarkable. So what I want to do in this video is to ask a few questions about this and see where we can get to in terms of understanding. So let's, for a moment, just pause the screenshot. I said that at a conceptual level, human beings literally look at the screen, move the paddle. That's all there is to it. And in a way, this implementation does exactly that for the computer. To repeat, if it was being given a set of instructions based upon knowledge of where the ball was and told to move the paddle in response to that, that would be an algorithmic approach. That would be what we would call a model of how the game works. But that's not how this is done. This is done by a piece of software that takes the screen position, reads it, feeds it into a neural net, as I say, based on a TensorFlow design, which feeds back to it what is in effect an instruction saying move the paddle here or there. If you look at the game, and we're just going to go back in a second, I'm sorry it's a little bit jerky, but this is a limitation of computer power. It doesn't look jerky if you see it for real, as you might say. If we go back to the game and consider it, you'll see that the paddle doesn't just move at the last minute. It adjusts its position almost as though it were anticipating where the ball would come from, given the position it was in when it returned the ball to the opposition. So let's have a look at that again. That's the red paddle. Now the white paddle hits the ball now, and you can see it goes down slightly, and it waits for the ball in approximately the right position. The ball then goes back. It anticipates that it still needs to be at the bottom of the screen, so it stays at the bottom of the screen. This time, it moves up because it thinks that it's hit the ball in a slightly different way, and the position of the ball on the screen indicates that it's likely to reappear higher up than it was when it was hit. How does it work? Well, it's one thing to make someone else's software run, and that's not altogether easy, believe me, because you have to install all kinds of software before it will run. But even when you have it running, it's interesting to ask how it works. And it's far from simple, but that it works at all is remarkable, and that it works by, in effect, looking at the screen and responding appropriately is the most remarkable thing of all. Good evening. It's dark outside, but if you followed the earlier video about Pong, you will remember that the computer was learning to play just by sampling the screen rather than by doing its explicit instructions or algorithms. Well, this being so, it struck me that it ought to be possible to change the game and have the AI system learn it anyway. So I thought, well, why don't we put an obstacle in the middle of the Pong screen and then see whether it can learn how to play when the ball bounces off the object. It's been playing for about 2 hours, and it's, well, I'm not sure it's doing terribly well, but it's having a go. You can see that there's a green blob in the middle of the screen, just to make it more difficult, and that if the ball hits the blob, it bounces off it. Now, the evil AI on the right with the red paddle is, of course, cheating, because it simply follows the vertical coordinate of the ball so that the ball strikes it in the middle of the paddle. On the left, the white paddle is trying to predict the behavior of the ball, but of course it's quite a lot more difficult, in as much as there is now a green object that can obstruct the path of the ball and make it go a different way. But if you look carefully, you'll see that there are moments when the white paddle gets it right, such as that, and then the red paddle sends it back, but the white paddle doesn't respond. But there it responded properly to something bouncing off. Here it looks as though it's going to manage. And you can see that its score at 2,565 is really quite respectable, given that it's a game that has just been made up randomly and that there is no strategy. I suspect that by tweaking the way the model is set up, this particular version may need a little bit more by way of memory. It may mean that you have to store more information for the sampling process. And there may be all sorts of other ways that it can be tweaked to make it work better. But it's doing pretty well. It's done about 250,000 iterations at the moment, and it's scoring some points. So that confirms that using image sampling with no explicit instructions as to how the game should be played is tractable. And if you can do it on a fairly old and slow Mac laptop, then obviously you can do it far better on a really fast, powerful machine. My experiment adding an extra obstacle between the two paddles in the Pong game and then expecting the AI to learn how to play it has been remarkably successful. At first, I didn't think it would ever get the hang of it, but it's now done something like 350 iterations, and this is the result. The ball occasionally bounces off the green square, and that obviously adds an extra element of unpredictability to the whole process. But now, after, what is it? Yes, something like just over 350,000 iterations, the white paddle has got the hang of it. And as far as I can see, I've been watching it for a little while, it's playing more or less perfect Pong. There's the ball bouncing off the obstacle. And the white paddle is having to move quite a long way sometimes to correct, particularly if there is a collision with the green square. Seems to have got into rather a predictable pattern at the moment, but it does eventually alter. There we are. And remember, this has been shown nothing about this game except the screenshots and the score. The score constitutes the reward that reinforcement learning expects, And essentially the search looks for ways to maximize the score by anticipating the right place to put the paddle in order to keep it in play. So it seems that the claims being made for this are true. I'll think about adding extra obstacles and training it again. 350,000 is not that many. And of course, it's running quite slowly on a fairly low-powered computer by modern standards. So we can say that the experiment has been successful. Thank you for watching, and good night.